Okay, so for those of you who are not familiar with RL, I'll just give a brief background about it. So it's easier to understand RL from an objective of a human. We can think of a brain as an agent which is trying to learn from its environment and trying to be more intelligent in order to achieve a particular objective. So the brain perceives information from its surroundings using its sensory organs, and essentially it uses those sensory information to make some kind of a decision in order to take and finally execute it into an action. Now once an action has been executed, the brain expects some kind of a feedback from the environment which tells how good or bad that particular action was, and this entire setup can be thought in an R can be thought of an RL framework. So at any particular time instant, an agent receives an observation OT, it executes an action AT, and finally receives a reward RT. In case of an environment, the environment executes the action AT, emits an observation that the agent would undertake in the next time step, and finally also emits the reward that the agent would require in order to understand how good or bad the action was. In most of the RL settings, or at least in our case, we treat the framework as an episodic framework where each episode progresses with one time step. We are all surrounded by multi-agent systems in the current world. If you look at traffic, we are essentially competing with other vehicles that are there on the road. In case of the economy, every corporate sector is also competing with its competitor. Similarly, in a market setting, it's a little more complex where you compete with your competitors but also cooperate with your customers and so on. However, cooperation is not so easily learned. It's a complex behavior which is governed by a lot of social norms and other rules that we are not particularly aware of or that cannot be put into equations. So the eventual question that arises is, how can we make multi-agent systems cooperate? Before we dive deeper into what we have been building all this while, I want to highlight a few challenges in multi-agent reinforcement learning. First challenge is the curse of dimensionality. That is, since most of the agents are trained using the neural network requires some kind of an input. In case of a multi-agent setting, the input comes from each of the agent that is present in the multi-agent system. So as you see, if we increase the number of agents in the multi-agent systems, the input size also increases, and thus we are to deal with the curse of dimensionality in large multi-agent systems. The second highlighting problem is specifying a good learning objective. Now the issue with a good learning objective is that since you take a particular action, you would want to essentially know how good or bad the action is. But if your objective is not good enough or is not giving you an appropriate feedback based on the action that you have undertaken, it's very likely that you might just learn a suboptimal policy or behavior that might not be suitable to actually execute that, to actually attain a particular objective or goal that you have set to achieve. And finally, we have the credit assignment problem. So credit assignment, I would want to discuss more about the credit assignment problem in an analogy. So firstly, the credit assignment problem is a problem of determining the actions that lead to a certain outcome. So for example, in a game of football, at each second, each football player takes an action. In this context, an action can either be passing the ball, dribbling the ball, running, or shooting the ball. At the end of the match, the outcome can either be a victory, a loss, or a tie for a team, right? And after the match, usually we have coaches that talks to the players and analyzes the match and performance of each player. He usually discusses the contribution of each player to the result of the match. The problem of determining the contribution of each player to the result of the match is the credit assignment problem. Now, why is it relevant to RL? You would say it's essentially in order to maximize the reward in the longer run, the agent needs to determine which actions will eventually lead to such outcomes, which is very essential in the credit assignment problem, which is essentially the credit assignment problem. Like, you would essentially want to know what particular action is driving the agent to a particular outcome. Now, in large teams, you would probably understand that credit assignment is pretty difficult, because you just don't have to mind your own actions, but you also have to mind the actions that other agents have taken. So when you're cooperating, it would be very likely that an action of other agent has actually helped you achieve your own goal. So we address the credit assignment problem with partial reward decoupling, which I'll talk a lot in the later slides. But to give you a gist, with PRD, what we are trying to achieve is, instead of dealing with the entire large ecosystem of multi-agent system as a whole, we are trying to break it down into subsets of problems, or basically decoupled sub-problems, which essentially would help us simplify the credit assignment problem. So if you have a system of around 100 agents, instead of dealing with all the 100 agents, we want to deal with just 10 agents, because that makes the credit assignment problem easier. So we use the actor critic method in our approach. I'll talk a little more about what actor critics are. So essentially, an actor is responsible to learn a behavior or a policy which would yield a maximal reward in order to achieve a particular goal. In case of a critic, its responsibility is to critique the action that the actor has taken and rectify it, or basically allow it to grow in a particular way that would allow the actor to achieve, or that would basically make the actor capable to achieve a particular goal that is set out to achieve. So essentially, it would force the actor to take the most favorable action in order to achieve the goal. Now coming back to credit assignment problem as a variance problem. So from a multi-agent RL perspective, if we assume that there are m agents in a particular environment, we can basically write the policy gradient in an actor critic faction. The policy gradient in an actor critic faction can be written in the following way. So for a particular agent I, we have the gradient for the policy as the expectation of the log of the policy, that is taking a particular action given the current state, multiplied by the advantages. So the advantage terms essentially measure the influence of each agent I on each other agent's future reward. So if the credit assignment is happening in a perfect fashion, the advantages would be noise free. However, that is not really true in a large ecosystem of multi-agent systems. So the variance of PG therefore tends to increase as we increase the number of agents in the multi-agent systems. That is, these advantage terms would essentially rise. And if you have a lot of agents that do not offer that do not have actions that have a direct influence on your reward, you will have a lot of more noise in your gradients than a lot of more actual feedback that you would require to make a valuable update. So what is the motivation for partial reward decoupling? So in multi-agent systems, usually it's explicitly enforced that all agents cooperate with every other agent present in the system. But if you look at it, that's not actually that shouldn't be happening, right? Like, it shouldn't be true that every agent needs to cooperate with every other agent at every particular time step. So if you look at this particular example, we have 4 agents at a crossroad. The 2 orange cars, they are likely to collide. Hence, these 2 cars should only pay attention to each other, or basically pay attention to the actions that these 2 agents are taking, and not worry about the actions that the blue cars are taking. So what essentially has to happen is that the 2 orange cars need to cooperate with each other and just marginalize the blue cars. And similarly, for the blue cars, they need to essentially cooperate with each other and not care about the orange cars. But that essentially doesn't happen in a cooperative setting in multi-agent systems. We enforce that every car is essentially cooperating with every other car, and that brings in a lot of noise, because when you're focusing on other agents that are not essentially required, you have unnecessary information to make a particular decision, and that brings in a lot of noise in the gradient update. So if at all this orange car is asked to only pay attention to this other orange car, the advantage terms in the policy gradient updates can ditch the advantages that are coming from the blue car. Hence, we are balancing or increasing the ratio between signal to noise in a particular way, if you look at it. So essentially, we can get rid of these terms, which are corresponding to the blue car from the orange car's perspective. So we define the relevant set of agent I at time t as a set of other agents whose expected future rewards depend on the actions of agent I at time t. So to calculate the Q function for a particular agent j given the current state and action, it can be written as the expected sum of future rewards of agent j given the current state, all the actions of other agents and the actions of itself and the policy. However, we can also write it as the expected sum of future rewards of agent j given the current state t and the actions of all the agents that are lying in the relevant set of agent j. So essentially you're ditching the actions of all the other agents that are not responsible or that are not contributing to the rewards that agent j is receiving at any particular given time. And hence that leads to this particular Q function, which is equivalent to the actual Q function. So when you write the PRD actor critic update, you have the same old policy gradient, wherein the advantages, the sum of the advantages only incorporate advantages coming only from the relevant set of agents and not other set of agents. Now the practical question is, how do you determine this relevant set? How do you know, or how do you realize which agents are actually helping you in order to achieve your goal and which agents are not helping you achieving your goal? And if you look at it, this analogy can also be drawn from a human perspective. I tend to take, or I desire to take a lot of inspiration from psychology. If you look at humans, a human will always have a close set of friends who are essentially helping each other achieve their own goal, and other friends are act as acquaintances. Their opinions don't really matter. So this kind of a setting can also be incorporated with the transformer architecture using the attention mechanism. So in our critic method, our critic network looks something like this, where we have a state action embedding which receives the states and actions of every agent, and then we have a key and query network which receives the states of every other agent. Now we use the keys and the queries to perform a dot product, which gives us the weights that each agent assigns to every other agent, including itself. Now, if the weight pertaining to a particular agent is high, that means that agent's actions is contributing a lot more in order is contributing a lot more for a particular agent to basically maximize its reward and essentially achieve its objective. And why is it intuitive? Because the value function is essentially telling you how much will you maximize your future reward, or is it essentially telling you that given a particular state, what's the likelihood, or what's the maximum action, it's the sum of action, the sum of rewards that you would get at the termination of a particular episode. So when an agent is contributing more, and we are learning this in a data driven way, and if the agent's actions is contributing more, it would have a higher weight value assigned to it, because that information would essentially be useful to predict the maximal future rewards that a particular agent can get. And if an agent's weight value, if the weight value pertaining to a particular agent is less, that means that we can kind of intuitively say that agent's actions do not have any influence on the current agent's rewards. And that is what we are trying to achieve. We are ditching those connections or weight values which lie below a particular threshold. and that threshold needs to be set manually. Essentially, in our experiments, we'd set the threshold to be 1 upon the total number of agents, because you would essentially want to. So when you start off the transformer network, you have uniform distribution of weights. So essentially, you would want to have all agents be a part of your relevant set at the very beginning, and then slowly narrow down and figure out the relevant set of agents that truly contribute to your rewards. So you're basically shutting off all the other connections that are coming from agents whose actions have no influence on your rewards whatsoever. Now we kind of delve into the experiments that we did in order to validate our hypothesis and intuition. So we evaluated PRD, and PRD is learning efficiency and asymptotic performance, by comparing it with other 3 baselines. One of the baselines was greedy actor critic, where each agent was attempting to maximize its own reward and not care about other agents. It's a totally greedy setting where you're solely competing with other agents. In case of shared reward actor critic, every agent was trying to maximize every other agent's rewards, including itself. So it's trying to cooperate with every other agent, which is the case in normal multi-agent systems. And comma, which is another algorithm that deals with credit assignment implicitly. That is it. How, like, we are essentially realizing the set of agents that lie in the relevant set explicitly, comma does it implicitly. And we test all these algorithms, like these baselines with our algorithm, on the following environments. So the pair agent goal finding environment is essentially an environment where 2 agents are paired with each other, and by paired I mean that agent 1 and agent 2 are paired when agent 1 when agent 1 receives the reward of agent 2, and agent 2 receives the reward of agent 1. So essentially they need to cooperate with each other and have the advantages terms shared with each other in order to know what their true reward is. In collision avoidance, it's pretty straightforward. Like, every agent is trying to reach to its goal location, and they need to avoid colliding with every other agent. And then there's social dilemma, where every agent receives a particular reward depending on the goal that they get to, but further they are divided into teams. So like, there are 2 set of teams. One set of team has a set of goal locations, and the other set of team has another set of goal locations. However, they don't know what their goal locations are, but they need to figure out what their goal location is. But the caveat to this problem is that if there are 2 teams, team 1 and team 2, and team 1 has goal location G1 and team 2 has goal locations G2, if any of the team member from T1 goes to the goal location G2, the other agents get penalized, but the other agents from team 2 gets penalized, but the agents from team 1 get rewarded. However, what you would essentially want to do is maximize the reward of all the other agents, like for all the group, that's the objective of the environment. You would essentially want to maximize the group's reward. So essentially, every team would want to move towards the goal location of their own team and not the other team in order to do that. So these are the experiments which we ran. So collision avoidance V1, V2, V3, there are different variants of the collision environment, and as you can see, like, PRD either performs as well as other agents or superiorly outperforms the other agents in most cases. We ran another experiment. So now that we are removing or chucking out agents that do not offer any kind of benefit to the current agent in order to achieve its goal, we are essentially reducing the variance in the policy gradient terms, right? So the essential experiment to run was to see how training time gets affected. Now, if you have a good signal to noise ratio in the policy gradient updates, that means your network is learning something meaningful and it's able to learn that very quickly. and that essentially what happens. If you look at PRDAC and shared AC was the one which uh, like it was already like it was explicitly enforced for all agents to cooperate with other agents. The signal to noise ratio is very low. Like the variance in the gradients is pretty high. That's what it says. And similarly, in PRDAs, like on the contrary, PRDAC's variance is pretty low. So the lower the variance, the better for you to learn, because if your variance is high, the updates are going to be very noisy, and it's very likely that you might just end up in a local optimum. So this was most of our work. Sorry. Uh, in the future, we plan to integrate PRD with other state-of-the-art algorithms such as PPO. Another drawback, so one of the drawbacks of PRD is that it can only be applied to online actor-critic methods. We also want to apply this to offline actor-critic methods. We also want to deal with sparse attention in a way, because if you look at it, even though we are dividing, if you're looking at soft attention mechanisms, like here, we are still giving some kind of attention to agents that are not contributing to the goal of the current agent. There's still some attention going towards them. However, it doesn't matter how small it is, but cumulatively, if we have a if in a pool of large number of agents, if we are only cooperating with a handful of agents, we are still dividing our attention onto other agents. We don't want that to happen. We want attention to only be given to agents that are relevant to the current agent, and no attention should be given to irrelevant agents. So one way to go about that would be to introduce a hard attention mechanism followed by a soft attention mechanism, where the hard attention mechanism shuns off all the connections that are going to irrelevant agents, and then we have a soft attention mechanism which gives importance to each other agent. So essentially you have a small pool of relevant agents, and then again you're handpicking which agent's action has had more contribution and which agent's actions has lesser contribution. Although every agent's actions would have had some contribution, we are still giving them importance in a way, and that could better that could basically be a better approach to address a credit assignment problem. And yeah, finally, the applications of PRD to domains other than RL, such as traditional multi-agent planning algorithms. Yeah. Okay. Yep. Thank you so much. Oh, before I end, I'm really sorry I couldn't be like present for this presentation. Like I actually wanted to be present. I've been traveling, so it's been a little difficult. Thank you all. I hope you have a good learning session in this symposium.